We will continue with problems. The last problem we solved in last class was let R be a ring. Show that R is a field if and only if the only ideals in R are the zero ideal and the ring itself. Then, as part of that problem, the continuation of that problem, we have the I verbally said this, but I'll write it down. Let phi from R to R prime be a ring homomorphism. If R is a field, then phi is injected. And the solution was that the kernel of phi is an ideal of R, but R is a field, and we saw from the previous problem that R is a field, its only ideals are the zero ideal and the field itself. So this implies that the kernel is the zero ideal or the kernel is the entire field. But we know that phi of 1 must be 1. So 1 does not belong to the kernel. Therefore, the kernel is not the entire field. So we can say kernel of phi is contains only the zero element. And by one of the previous problems, the kernel contains only the zero element only if phi is injected. So there are only injective ring homomorphisms from a field to a ring. Kernel of so a ring homomorphism is also a group homomorphism of the additive group, right? So because phi of a plus b is equal to phi of a plus p of b is one of the conditions for the homomorphism to be a ring homomorphism, but that is a necessary and sufficient condition for the homomorphism to be a group homomorphism. So once it is a group homomorphism, the kernel is an additive subgroup of the domain. Yes. And in the group homomorphism, when we are looking at that, we proved that the kernel is a subgroup of the uh, domain group. So here also, since ring homomorphism is also a additive group homomorphism, the kernel is a additive subgroup of the of R plus, which is the first condition for a set to be an ideal, right? Phi is an ideal, it has to be additive subgroup of the ring. That's the first condition. Second condition was that if you take one element from the ideal and some element from the ring, whether it is in the ideal or not, you take their product, that should also be in the ideal. But that is always true. What does it mean for an element to be in the ideal? Suppose A is in the kernel of phi. That means phi of A is 0. Right? Take any other ring element R. What is phi of R into A? This is by definition of the homomorphism equal to phi of R into phi of A. But phi of A is 0. So this is 0. So RA is also in the kernel. Any element which goes to 0 is in the kernel. So for any ring element R and any ideal kernel element A, their product is also in the kernel. So now both the conditions for the ideal are satisfied, right? Yeah. So regardless of what the domain ring and codomain ring are, and regardless of what the homomorphism actually is, its kernel will always be an ideal of the domain ring. And if it happens that the domain is a field instead of a ring, then the homomorphism has to be injected. That is, one if some element goes to one image, no other element can go to the same image. Different elements go to different images. And next question is, it is on ideals. Let R be a ring. Let I and J be ideals in R. We'll define two new sets. I intersection J is a set of all elements in the ring that are in both I and J. The other set I union J is a set of all A such that A is in I or A is in J or it is in both. Are both of these ideals, or which of these are ideals? Yes, actually, I think we solved that in one of the problems. The intersection of two subgroups H and K, H intersection K, is also a subgroup of a group G. Yes. So um, I intersection J is an additive subgroup of R. This comes from group theory. Then suppose A belongs to I intersection J and R is in R. Since RA is in I and A belongs to I intersection J means that A is in I and A is in J, but both are ideals. So for any ring element, RA is in I and RA is in J. So RA is in I intersection J. So I intersection J is an ideal. I union J need not be an ideal. Because, for example, suppose consider the ring R is equal to set of integers, then all ideals are of the form nz, where n is a non-negative number that we saw in one of the previous classes. So consider I is equal to 2z, j is equal to 3z. I is all multiples of 2 or j is all multiples of 3. Take the union I union j. This does not contain the element 5, but it contains 2 and 3. So it is not an additive subgroup of Z. If it is an additive subgroup, it has to be closed under addition, but it is not closed under addition. So this is like taking two straight lines, the x and y axis, and taking only the points on x and y axis. That is not a subspace, right? You have to consider all the sums of the points on the two straight lines to get a subspace. So a plane passing through two intersecting lines would be a subspace consisting those lines. But simply taking only the points on the lines will not give you a subspace. It is something like that. So R union J would not be an ideal, but what if you wanted to construct an ideal with I and J, similar to how you can take the sum of all vectors on both the lines. If you take it, that is the plane passing through two straight lines, you would get a subspace of if you are in R3. In R3, the subspaces are the origin itself, entire R3, lines passing through the origin, and a planes passing through origin are all subspaces of R3. If you took two straight lines passing through the origin, two different straight lines, and consider the plane containing those two straight lines, then that would be a subspace passing through the origin, and it would be it would be a subspace. So similar to that, we can construct a subspace, not a subspace, an ideal using I and J. So instead of doing I union J, what you do is you take, we'll call this I plus J. And we'll define it to be A plus B, A in I, B in J. Now, can you show that this is an ideal? Yeah, it is an ideal, but how will you prove it? You have to show all the properties. So if you have two elements, first we'll show closure. We have A plus B and C plus D. If you add these, then you can always write it as, since this we are only dealing with commutative rings. Um, no, even if it is not a commutative ring, the addition operation is commutative, even in other types of rings. So addition, it has to be an abelian group, even if it is a non-commutative ring and even if it doesn't have identity. So because of commutativity of addition, we can rearrange this and write it as A plus C plus B plus D. Since I and J are ideals, A plus C is an element of I because A and C are elements of I. So this belongs to I. Since I is an ideal, it is also a subgroup under addition. So it is closed under addition. Similarly, B plus D belongs to J. So the sum of two elements in I plus J belongs to I plus J. This belongs to I plus J. So it is closed. Then, since they are additive subgroups, 0 belongs to I and J. So 0 plus 0 equals 0 belongs to I plus J. 0 can be written as 0 plus 0, where for the first 0 you consider coming from I, second 0 you consider it as coming from J. So we have the identity. Then commutativity and associativity we need not check. We are assuming these are elements from a ring. It's a subset of a ring. Inverse is simply uh, if A plus B belongs to I plus J, then A belongs to I, B belongs to J, I and J are additive subgroups, so minus A belongs to I, minus B belongs to J. So minus A minus B, which is equal to minus of A plus B, belongs to I plus J. So we have the additive inverse. Therefore, I plus J is a subgroup of R plus. The second property is that if suppose A plus B belongs to I plus J, that is A is in I and B is in J, let R be any element in the ring. R into A plus B is by distributive property RA plus RB. But since I is an ideal, RA belongs to I. Since J is an ideal, RB belongs to J. So this belongs to I plus J. Therefore, I plus J is an ideal of R. Also, I plus J, I union J is a subset of I plus J. Is that clear? See, you have to. Okay, explain. What part you didn't understand? Union is simply taking all elements in I and all elements in J. You are not allowed to add elements in I and J. those elements won't be in the union. No, you can always add 0 from the other set. Yes, you can take A in I and 0 in J, then you can add them, you'll get A plus 0 A, which is in I. So I is also contained in I plus J, J is also contained in I plus J. That's why 0 is should always be there, since it is a subgroup also. Similar to even in straight lines in R3, every plane is not a subspace of R3, right? Only planes passing through the origin are subspaces of R3. Similarly, only straight lines passing through the origin are subspaces of R3. So it must always contain the origin. Similarly, here the equivalent is it must always contain the additive identity. This is for general rings. For any ring, this will hold true. When you come to a specific example of integer ring, suppose I is, so we use this notation to denote the subgroup generated by A when we are dealing with group theory. Here, when we are dealing with rings, it will simply be the ideal generated by A. And the ideal generated by A is simply the product of all elements uh, in the ring with A will also be included in it. Yeah, no, this is different. We defined it in last or the previous class, last class or the one before that, I don't remember. We defined the ideal generated by an element. Ideal generated by the element. A is an element of R, then the ideal generated by A is the set of all R A such that R is a ring element. No, we don't have an ideal, right? We started out with an element in the ring and we constructed an ideal. But how do you construct that? There's no standard method of constructing that. Most of the time, you are given some set and you are asked to prove whether it is an ideal or not. So there's no standard method to give form an ideal. This is one way of getting an ideal. You took the ring Z, you picked the element A is equal to 2 belongs to Z, then you multiplied all elements of the ring by that element. You get 2Z. 2Z is an ideal now. No, a single element, how can it be an ideal? That is the generator. We are defining this quantity called the ideal generated by an element. Like how we defined the subgroup generated by an element as the powers of the element. Similarly, we are defining the ideal generated by an element by the product of the element with all the ring elements. Yes, any element in this, I left that as an exercise, but I'll do it. First, we have to prove that it is an additive subgroup. You take R1A and you take R2A. These are two different elements, right? This is all products of A. So you have to take two different ring elements to get two different elements in this set. And you add them, you get R1A plus R2A, which is by distributivity R1 plus R2 into A. But since R is a ring, R1 plus R2 is another ring element. So it is of the form some ring element into A. So this belongs to the set RA. It is of that form, right? So this is closed. Then you can always take 0 in the ring and multiply that with A, you will get 0. So 0 belongs to this set. Then if you have R1A, you can always take the negative of that and multiply with A. And we showed in one of the problems that this will be equal to minus of R1A. So if you have R1A, you have its additive inverse also. So this is an additive subgroup. Then pick any ring element R, any element in the set. Their product R into R1A is simply equal to R into R1 into A. This is simply equal to R2A for some other ring element R2 in R by closure. R1 R into R1 is also a ring element because the ring is closed under multiplication. But R2A will also be an element of this set generated by A, right? So this for any ring element R and any element in this set, its product belongs to A. So this set that was generated by A is an ideal of R. This is true for any ring R, and by picking any element A in the ring, you can get an ideal. And we call this particular ideal as the ideal generated by the element, by that particular element. So in the case of integers, what will happen is if you take any element and multiply it with the set of all integers, you will get simply the multiples of that element. If you pick 2, you get multiples of 2. That is an ideal, and we saw that earlier through other means also. So a different proof that nz is an ideal for any n. Yeah. So now coming back to the original thing, if consider the ring of integers, let I be, you pick one element A, some integer A, let I be the ideal generated by that A, and let J be the ideal generated by some other element B. Now you do I plus j, which is the set of all elements formed by taking sum of elements in I and sum of one element in I and another element in j. Can you say something about this without knowing exactly what A and B are? We had this division GCD theorem, right? Yeah. Yeah. So GCD is the smallest positive integer that can be written in the form of R1A plus R2B. And as subgroups, we know that any subgroup uh, of the integers can be written in the form of dz, where d is the smallest positive integer in that set, right? So you take this will simply be the GCD of A and B, all multiples of that. This will simply be the subgroup generated by GCD of A and B. If it so happens that A and B are relatively prime, their GCD will be 1. And the ideal generated by 1 is simply the entire set of integers. So if A and B are coprime, what you get by adding these two will be the entire set of integers. Then we added two elements and got an ideal. What about multiplying two elements, each taken from one of the ideals? Let I and j be ideals of a ring R. I plus j we already defined. Suppose we define I into j. If I simply defined it as AB, where A is in I and B is in j, would it be an ideal? At least is this guarantee directly? Is there any guarantee? Huh. Yes, first closure, we'll always start with closure. Is that closed? That's not obvious, right? We don't know. Um, it looks like it's, I mean, we can give counter examples later, but it looks like it won't be. Uh, there's no guarantee that AB plus CD will be a product of some element in I and some element in J, right? So this simple definition will not give an ideal, but we can change this a little bit by writing it as sum of all AI BI, where each AI is in I and each BI is in J, and this is a finite sum. Or you can write this as I is equal to 1 to n, and n is some natural number. This be an ideal now? No, you can take as many terms in this sum as you want. N can be any natural number, so it can be 1, 2, 3. So you can take simply the product of A and B, where A is in I or and B is in J, or you can take two such products and add them, or you can take three such products and then add them. So you can add an arbitrary number of products. Yeah. So if you take one of the elements of the form A1, B1 plus etc. A and Bn and add it to another element of this form. At the end of the day, this is simply of the form. There will simply be m plus n term. That's all. It's very trivial because we are allowing the addition of any number of terms of the form A, B, where A is in I and B is in J. So if we add n such terms to m such terms, you will simply have m plus n terms of that form. So this will be closed under addition and then minus a1 b1 minus a2 b2. This will also belong to ij because simply you can take however you want. You can take minus a1 in place of a1 or minus b1 or in each of the terms one of them you can simply negate and that will also belong to the corresponding ideal. So if a1 is in I, minus a1 is in I, and if b1 is in j, minus b1 is in j. So you can take minus a1 times b1 or a1 times minus b1. Both will give you minus of a1 times b1 only. So the additive inverse is also in ij. You can always pick 0 times 0 because 0 is in I and 0 is in j. So 0 belongs to ij. This way, of course, we have to check associativity and commutativity, but we simply say that it is inherited from the ring. So this is an additive subgroup. Then, if you take some element R in R and take the product with one of these elements, you will get RA1 B1 plus etc. R, A, N, B, N, but I is an ideal. So this will simply be A1 prime B1 plus etc. N prime Bn. Where each of the AI primes belongs to the ideal I because each of the AIs is in I, R times each of the AIs is in I. So this will also belong to Ij. Therefore, Ij is an ideal. So you can't simply take I elements from I and elements from J and multiply that. That would not be an ideal. But you can take the sum of all such terms, sum of arbitrary number of such terms, and that will give you an ideal. So, for example, you had R is a set of integers. The ideal I is 2z, ideal j is 3z. We had I plus j is the GCD of 2 and 3, the multiples of GCD of 2 and 3. So it is since 2 and 3 are co-prime, I plus j is simply z, and ij is what will ij be? Linear combination of products. That sum of products. So one first term should be from 2z, so it should be a multiple of 2. Second term is from 3z, so it's a multiple of 3. So each product will be a multiple of 2 into 3. Oh, here, here. So it will be 6z. In this case, what is I intersection there? J. Yes, I is set of all multiples of 2, J is set of all multiples of 3. Intersection are elements contained in both I and J. So they have to be both multiples of 2 and multiples of 3. And that is only possible if they are multiples of 6. So this is also 6z. But this is not always the case. So only in this case, I intersection J, okay, that logic is true, but I intersection J is not equal to I plus J, I into J all the time. For example, consider I is 2z and J is 4z. Now what is IJ? Actually, it's not, IJ is not the LCM times, it's not the LCM into Z. How? Uh, 2z will contain 6. Does ij contain 6? Can you write it as an element of I and into an element of j, or the sum of those things? And it can't be 2z. Yes, ij is 8z. So ij, so it is not the LCM. I intersection j is the one with the LCM. I intersection j is 4z. If you take all multiples of 2, minus 4, minus 2, 0, 2, 4, 6, 8, etc. Minus 6, minus 8. And you take all multiples of 4, 0, 4, 8, minus 4, minus 8. You take the intersection, you are left with all multiples of 4. Intersection is simply the common elements in both the sets. So you are left with 4z. That is the intersection. But if you take all products or sum of products from both the sets, then you have 0 into 0, then you have 2 into 4, 8, 2 into 8, 16, then you have 4 into 4, 16, 4 into 8, 32, 6 into 4, 24, etc. These are all multiples of 8. First element is a multiple of 2, second element is a multiple of 4. So their product will be a multiple of 8. No? 2a into 4b is 8ab, which is a multiple of 8. So ij is, in this case, only for integers. This is not how it works for all general rings. But in the case of integers, since the ideals are all of the form nz, if I is az and j is bz, then ij is ab into z. I intersection j is LCM of ab into z. I plus j is GCD of a plus b into z. Is that okay? Any confusion in that? Okay. Next is, so these are things relating ideals of the domain and the ideals of the codomain. Suppose phi is a ring homomorphism. First part is if I prime is a ideal. So we have an ideal of the codomain. Then phi inverse of I prime. So this is a set inverse. Is an ideal of R. Set inverse is understood, right? No, no. The inverse has, instead of in taking the inverse of each element, it is okay. If you have A, B, C, D, E, F, G, Suppose this is the function, then the inverse of the set EF is all elements that go to EF. So it is P inverse of EF is ABC. So P inverse of simply D is what? Yeah, so it's the null set. Similarly, P inverse of DE would be B is also mapping to E. All the A is mapped to E and B is mapped to E. So this is AB. Yeah, the P inverse of F G would be, yeah. So instead of, so here it's not a bijective function, so you can't take the inverse of one element. Phi inverse of E, if you took it as the function inverse, it doesn't make any sense, right? Because A and B both are mapping to E. So which one is the inverse? Phi inverse is also a function, so it can only give you one output. Yeah, so it can't, you don't have a function inverse because it's not a bijective function. So in this case, we define the set inverse. So the inverse of a set in the codomain is simply the set of all elements in a domain whose image lies within that codomain set. So now if this is R prime and this is R, you take a subset here, I prime, which is an ideal of R, and here you consider all the elements that are mapping onto I prime, elements in I prime. You call that I. Turns out that I will be an ideal of R. That is what this claim is saying. So first we have to check closure. Suppose A and B belong to phi inverse of I prime. That actually means that phi of A is in I prime and phi of B is in I prime, right? These are elements whose image is in I prime. But then phi of A plus phi of B is in I prime because I prime is an ideal. So an ideal is also a subgroup, additive subgroup. But by the ring homomorphism property, this is simply phi of A plus B. So A plus B has its image in I prime. That means A plus B is in the inverse of I prime, right? So if A and B are in phi inverse of I prime, A plus B is in the phi inverse of I prime. So if A is in the phi inverse of I prime, then phi of A is in I prime, then minus phi of A is in I prime, minus phi of A is phi of minus A, so this is in I prime, which implies minus A is in P inverse of I prime. So you have checked the closure and additive inverse. Then we also know that E is mapped onto E. So P inverse of any ideal. So E R prime belongs to I prime because I prime is an ideal of R prime, right? And phi of ER is equal to ER prime. So ER will always belong to phi inverse of I prime for any ideal I prime. So it's a non-empty subset of R. Phi inverse of I prime is a non-empty subset of R, which is closed under addition and closed under taking the additive inverse. So by the two-step subgroup test, it is an additive subgroup of R. That part is clear, right? Then now to consider the second property of an ideal. Suppose A is in phi inverse of I prime and R is any arbitrary element in the ring. This would mean that phi of A is in I prime and phi of R is in R prime. R prime is the codomain. The image of any element of the domain is in the codomain. So this means phi of R into phi of A is in I prime because I prime is an ideal. We multiply any ideal element with a ring element, it is also in the ideal. But by the homomorphism property, this is phi of Ra. But this is just by definition of set inverse, this is in P inverse of I prime. So if A is in P inverse of I prime and R is in the ring R, RA is in P inverse of I prime. That's the second property for P inverse of I prime to be an ideal. So P inverse of I prime is an ideal of R. The other way around is not always true. It requires an additional condition. So we had an ideal in the codomain and we took its inverse. Uh, Inverse as set inverse and we got an ideal in the domain. Now again assume, now we have to assume phi is surjective, that is phi is on to R prime. That is every element of R prime is the image of some element in R. Might be the image of one or more elements in R. Now let I be an ideal. Then you take the image, the set image, P of I. This is an ideal of R prime. So phi of I is the set of all elements that are that the elements of I are mapped onto. That is A, B, C, D, E, F, G we had like this. Phi of the set AB is the set E, because both A and B are mapped onto E. Phi of set containing only C is the set F, because C is mapped onto F. Phi of the set ABC is EF. Yes. So if we take that. So the image of I, the set I, is simply the set of all images of elements in I. Now phi of I is an ideal of the codomain R prime. Proof is similar to the previous part. Again, we have to prove the same things. So E of R belongs to I because I is an ideal. P of E of R is E of R prime because P is a ring homomorphism, and that's one of the conditions. P of 1 should be equal to 1. And 1 and E we will use them interchangeably to mean the same thing. It's the multiplicative identity. So E of R prime belongs to P of I for any I. Therefore, Phi of I is non-empty. It contains the identity. Then for closure, suppose Phi of A and Phi of B belong to Phi of I. That is, pick two elements A and B such that their image is in two elements in. We are picking. So we are showing that Phi of I is an ideal. So we pick two elements in Phi of I. But Phi of I is what? It is a set of all images of elements in I. So it is a set of all Phi of A such that A is in I. So two elements would be phi of A and phi of B, where A and B are elements in the ideal. What is phi of A plus B? Sorry, what is phi of A plus phi of B? This is phi of A plus B because it is a ring homomorphism. Phi of A, phi of B are in phi of I implies that A is in I and B is in I. Correct? That means A plus B is in I. Right? So phi of A plus B is in phi of I. Correct? So we took phi of A and phi of B in phi of I. Then we showed that phi of A plus phi of B is also in phi of I. So we showed that it is closed under addition. Then if phi of A is in phi of I, then A is in I. This implies minus A is in I, which implies phi of minus A is in phi of I. But this implies minus phi of A is in phi of I. So this is a, yeah, it's a subgroup of the codomain additive subgroup with a two-step subgroup test. Then suppose R prime is an element of R dash, capital R prime, and phi of A is in phi of I. Now the surjective part comes into picture. Since phi is surjective, there exists some element R in R such that phi of R is equal to R prime. Correct, right? Therefore, R prime into phi of A is actually equal to phi of R into phi of A. This is equal to phi of R into A. Since I is an ideal, R is in R and A is in I. RA is also in I, which implies phi of RA is in phi of I. Therefore, R prime into phi of A, which is equal to phi of R into A, belongs to phi of I. So we have showed both conditions. Therefore, phi of I is an ideal of R prime. Yeah, this only happened because the phi is surjective. So third part is that image of an ideal need not be an ideal. For example, you have the homomorphism from the integers to the rationals given by phi of n is equal to n for all n in Z. This is the, what is this called? I had given a name, I think. From Z to Z, if you had this homomorphism, what would it be called? It's the identity, right? The identity function. No, no. It will simply be called identity homomorphism. That's all. If it is from Z to Z, so from Z to Q, it will be called the inclusion function. Yeah. So identity means it's actually a bijective function which maps an element to itself. But inclusion function is actually uh, it's a non-surjective function. It's injective, but it is not surjective. Here also the element in the domain is mapped to itself in the codomain, but the codomain is larger than the domain. So there are elements with no pre-image. There are elements in Q that won't have, that are not mapped onto by any element in Z. So such a type of function is called an inclusion function. So in this case, it is not a surjective function, right? For example, 2 by 3, there is no element, there is no integer that is mapped onto 2 by 3. So now, if you consider, Consider I is equal to 2z, which is an ideal of the domain. Phi of I is also 2z, right? Is this an ideal of rational numbers? Yes. Yes, yes. For example, if you multiply half by 2, 2 is an element of the set phi of I, half is an element of Q, half into 2 is 1, which is not as element of 2z. So 2z is not an ideal of Q. But another way you can reason this is Q is a field. The only ideals of Q are 0 and itself, since it is a field. We showed that last class. Yes. If R is a ring, the only ideals of R are 0 and itself, if and only if R is also a field. But 2z is not 0 ideal, it is not equal to Q. So 2z cannot be an ideal of Q, since Q is a field. But 2z is an ideal of the domain Z. So in this way, the image of an ideal need not be an ideal. The image of an ideal is an ideal only if the homomorphism is surjective. So that is required here for the when we are trying to prove the second property. Since phi is surjective, we can write every element R prime in the codomain as the image of some element in the domain. Only then we can proceed and show that R prime into phi of A is equal to phi of I belongs to phi of I. But in the other case, where we are taking the pre-image, phi prime is an ideal of R prime, then it does not phi does not need to be surjective. The pre-image of any ideal is an ideal, but the image of an ideal is an ideal only if the homomorphism is surjective. This is commutative algebra. No? Here our rings are commutative rings with unity. So our definitions of other things are also tailored to that. And here for us, for example, the ideal generated by A, I said it is set of all elements of an RA, where R is in R. This would also be equal to, this could have been written as R times A. This is also equal to A times R, because RA and IR are the same for us, because multiplication is commutative. But if it is not commutative, then these two are not equal. Yes, so what definition of ring and what definition of ideal you will use, that will depend on where you are applying it. But the concept will remain the same. Uh, but if you don't need it to be a subgroup, then yeah, some of the properties might change, or there might be additional results that won't hold in our definition. If you relax the conditions, some extra properties might hold, right? Yeah. For example, if you don't need it to be a subgroup, then the additive inverse, you can't assume that it exists in it, right? That will change a lot of things. So we'll stick with our definitions. Maybe when we revisit it um, later after the official course completion, if we continue with the lectures, that time maybe I will refer to a different source and we'll go with a more general definition. Maybe we'll do that. But then remembering all the results will be difficult. Anyway, we'll have the notes, you can just check depending on the situation. Okay, for notes I'll upload later. Uh, okay, I'll upload them later. We'll no, we'll have the next class on Monday. Tomorrow and day after we won't have it. On Monday we'll start with fields.